So I am doing seeing conditions for my first presentation ever at the Milwaukee Astronomical Society. We'll cover a lot today. Yeah, so I just thought I'd show you guys two images that were taken by some of the members of the Milwaukee Astronomical Society. The first one on the left is the Andromeda Galaxy by Gabe, and then the one on the right is the Witch Head Nebula and Rigel by Shibendu. So some topics we're going to be covering. First, obviously, the importance of a clear and, of course, dark night sky. Also, like quantifying seeing conditions, so like getting almost values like full width at half maximum, for example. And then also like how to detect poor seeing without technology. And then also light pollution, because light pollution we know exists pretty horribly where we live. I mean, Milwaukee is a Bortle 8 to 9, really more like a Bortle 9. And even the observatory itself is like a Bortle 7 or 8. We'll talk about the Bortle scale, magnitude, also limiting magnitude. We'll talk about light pollution's effects on signal noise ratio. Obviously, the more light pollution you have, the lower the signal noise ratio is, or like the less signal you have. And then also how to reduce its effect while imaging. We'll also talk about wind and like temporary setups and all that. I know that one of the topics that is going to eventually be covered that Gabe that was on the document that Gabe sent out to me was like a dome or retractable roof. I know we are going to have a presentation on that at some point. So I thought I'd add a little bit about why a dome or a retractable roof is better. And then also how poor seeing can affect imaging. We also have like the effects on planetary, lunar, and deep sky imaging, because the effects are not the same. I mean, it's different depending on what type of imaging you're doing, of course. Then also like star counts, signal noise ratio, and noise, among others. And then again, how to counter poor seeing while imaging. This is the M45, Messier 45. That was just a random picture I got online. So the importance of a clear and dark night sky, obviously, first of all, you have the visual beauty of a clear and dark night sky. I know that most of us have seen a dark night sky before. I know I have. And without a doubt, it is one of the most incredible experiences any human can experience. It is really incredible to see thousands of stars just above your head. And in a way, it's humbling as well. And then also our natural awe towards the night sky. Not even only our natural awe, but how we use it for navigation. Like we all know about Polaris and how it was used for navigation, basically navigation everywhere back in ancient times. And then also basically when you want good conditions for observing planets, stars, nebulae, and many other things. We've observed asteroids and variable stars in MAS, so there are a lot of things to observe. And then obviously you want a good clear night sky for that, because I mean, if you have a lot of atmospheric turbulence, you're not going to be able to have much of a chance to see, like for example, the features on Mars, which I was at the observatory like the day after Thanksgiving, I think it was, and unfortunately, the seeing conditions were terrible, so we weren't able to get a decent view of Mars. It was unfortunate, but Mars was still massive in the field of view for a scope. And then also imaging. So like imaging is obviously impossible without a clear sky and very difficult and expensive. We all know that because we live in light polluted areas and spend a lot of money on imaging equipment without a dark one. It's probably still expensive without a dark one. I mean, it is still expensive without a dark one, or with a dark night sky, but at the same time, it's probably less expensive, especially with light pollution filters and all that. But yeah, so this is just the Milky Way. You can see many different incredible features. Some that come to mind is Lagoon Nebula right below the core of the Milky Way. And then also to the very left, you have Rho Ophiuchi, which is a cloud complex in Scorpius. So some phenomena that determine seeing. Of course, you have atmospheric transparency. So this is like clouds and also haze. Like haze is specifically smoke from wildfires or like slash and burn agriculture, which is not really that prominent in Wisconsin, but I think of the developing countries, it is definitely not. It is definitely very prominent and can obviously pollute the sky with smoky haze. Then also air pollution. We live in the, I think it's the 24th. Yeah, we are the 24th in the nation in terms of pollution. So that can affect seeing conditions as well. And then also we saw in September with the smoke from the California wildfires because California itself was on fire. And we saw that we weren't really able to get any decent images during that time, obviously because of the haze, not the haze. Yeah, the haze. Um, but yeah, so uh, there's also fog. There's also fog. This is different than haze. Haze is different from fog. Fog is mainly caused by water vapor. It's basically occurs in times of very high humidity. Generally, it's 100% humidity. And basically, what occurs when fog is basically when water vapor condenses near the ground and basically forms clouds. Like we think of it as like clouds on the ground. It basically is that. But then there's also like water vapor. Water vapor kind of fogs the night sky in a way. So maybe not necessarily fog that reaches the ground, but like water vapor in the sky that obviously can affect the seeing conditions in an area. Obviously, there's humidity. You have higher saturation points, which is like the highest temperature or the highest, yeah, the highest temperature at which uh, water condenses into water condenses into, or no, water vapor condenses into water itself. Um, and then obviously on warmer nights, you have higher saturation points because there's a higher saturation point. And then you also have more water vapor and less atmospheric transparency. Then there's also wind. There's also convection in the atmosphere caused by unequal heating of these separate layers of the atmosphere and of same layers of the atmosphere, depending on how turbulent the day is. Um, that's known as atmospheric turbulence. And then there's also wind in general. Wind obviously affects imaging. I tried to image the Great Conjunction once, did not work. Then there's also light pollution, which we will cover in depth later. And then there's also the presence of satellites. This is a relatively new problem. I think of my parents. They tell me about how they didn't really see satellites ever when they were younger and when they were looking at the night sky themselves. Um, but it is certainly a new problem, and it is certainly an important one because I can see satellites from my own house almost every single night. And then there's also the Starlink satellites, which almost every astronomer on the planet hates, but thankfully they're doing something to fix it. I don't know if they're really going to fix it though. So this is just the picture on the right is basically an example that showcases turbulence. So the top is basically just overcorrection in the presence of turbulence. So you can see how it's just so unequal. You can see how basically the focus is just so unequal and so wavy and odd. It's almost like it's just messed up. It's fragmented in a way. But then you look on the quieter night in the overcorrection, you see that this is basically just blurring out the image, just focusing too far. You'll see that it's relatively similar. There's modest transparency problems. So this is an example. I'm sure some of you have seen this image already. This is an example of an image taken by astronomers. I'm not really sure. I can't not remember what telescope it was, but I think it was the European Southern Observatory. And they were taking images, and you can see that the Starlink satellites just completely corrupted the image, completely ruined the image. And obviously, we do astronomy from the ground for the most part right now. So these satellites are very conflicting with astronomical progress in a way, in scientific advancement. And then this is another example of satellites in the night sky. You're basically in a star trails image, you're taking like 15-second exposures at a time. And you'll see that these there are a bunch of different dots. They're all satellites. I think an unedited image like this has a particular significance. Like I think of my own images. I did a star trails image back in October at the observatory, and obviously we're pretty close to Mitchell in New Berlin. So the problem with that is obviously that you're gonna have planes and then of course satellites as well. So that definitely corrupts your images. So there are many different terms that took me a while to even rudimentarily understand that quantify seeing conditions. There's first of all we have the full width at half maximum. It's basically it's used with the coordinate system with Artesian coordinate systems in mathematics, and is used pretty much the same in astronomy. You can see the image in the top right. That's obviously full width of the function at half maximum, which is the half maximum light. Obviously, the maximum light is the vertex, the maximum of this function. It follows a function known as the Gaussian function. I didn't know what that was until I looked this up, until I did this presentation, until I formulated this presentation. So that was definitely interesting. It's basically the measurement of the quality of seeing based on how much a telescope and the atmosphere as well has smeared a point source, which is generally a star, but it's also just straight up a point in the image. Full width at half maximum is a function of the star's intensity, seen basically by the image in the top right corner on the slide. We briefly discussed this earlier. As I said, it resembles a function known as the Gaussian function. We'll show you the equation, or the function, not the equation, on the next slide. As you can see, it's basically the full width of the x values, which is the pixel position on the CCD based on this actual graph. It's the full width at half of the maximum of this function. So vertex, the vertex is the highest y coordinate on this graph, and you can see that this is going to be, that's maximum light, and obviously highest pixel value as well. So there you go. Yeah, and then there's also the R naught and the T naught. This was something on Wikipedia that just completely blinded me. It was it was not easy. So first of all, R naught is not like the R naught in healthcare. So a fair amount of us probably know about this because the R naught has to deal with infectiousness or infectiousness of a disease. So it basically indicates the transmissibility of a certain pathogen. It is basically indicated by the average number of transitions made by an infected individual. If the number is below 1, obviously the virus or the pathogen in general, so it could be a virus, it could be a bacterium, it could be a parasite, or really anything. As long as if the R naught is below 1, obviously the infection is going to be slowing down. Infections are slowing down. But if the R naught is above 1, which coronavirus is, of course, it's at I think 1.4. That's at mitigated levels. It's obviously spreading. But for the R naught in astronomy, it's basically it's also known as the Fried parameter. It corresponds to the length of spacing and actuators needed in an adaptive optic system. I'm not really sure what an adaptive optic system is, but we can certainly have discussions on that after my presentation is over. From what I've seen, it is basically a system that is built to minimize the effects of atmospheric turbulence and low transparency, of course. R naught basically corresponds to the spacing between the actuators at which atmospheric turbulence becomes significant. In the best observatories, the spacing is anywhere between 10 or 20 centimeters. And then there's also the T naught. The T naught is also known as the Greenwood frequency. It basically pertains to the frequency at which an adaptive optic system is required for optimal correction and mitigation of the effects of atmospheric turbulence. Overall, the T naught and R naught offer higher resolution, spacing, and shorter frequencies of correction when imaging in higher wavelengths. as longer wavelengths are often less affected by transparency and turbulence issues. I like to think of like the IR filter. I'm not sure if we have an IR filter at the observatory, but I know that we often use them for planetary imaging, and it can kind of bypass all the crazy turbulence that occurs and get you a higher quality image. They're very popular in planetary imaging. I'm sure uh, Damian Peach uses them. But yeah, and then there's also the Antoniadi scale. This refers to observation, but obviously it can be used for imaging as well. You can, I mean, many of us have telescopes. You can still probably, if you got an eyepiece for the telescope, you probably can figure it out, or you could use short exposures. So there are five different, there are five levels to it. So there's the first level, which is basically perfect seeing without a quiver. So like without just like a weird, like hot band in the image or in the field of view. And then number two is like a slight quivering of an image with moments of calm lasting several seconds. So it's still uh, very visible. I'd say the best we could possibly get to in Wisconsin, because it's humid here during the summertime. I'd say the best we can get to is probably a two. But in the deserts, of course, you probably can get to one. And then the three is moderate seeing with air tremors that can blur the image. That's probably more like what we would see in Wisconsin on average. And then four is like poor seeing, like a constant blurring of the image. Uh, we've seen that. I remember when I was at the observatory looking at Mars with Russ. I saw that same thing. Like it was constant air tremors that blurred the image. I couldn't see any details. Every single time I tried to see details, I would see these random blurs that would occur on the planet on Mars. Then and then there is five, which is basically terrible seeing in a very blurry image. This would be like the worst possible seeing outside of like completely cloudy. And then on the right, we have the airy discs, which this basically, the top one is basically what it should look like under good seeing conditions. This is a star. I think this was Capella, but I'm not really completely sure about that. I think it was Capella. I made this presentation like 2 months ago, so I'm not completely sure on what star that was. And then there's also this is just an inverted image of stars from an astronomical observatory, and you can obviously see that the airy disk is just completely blown out. So the diffraction obviously breaks up the airy disk into what are known as speckle patterns. So obviously they don't look that good. So this is basically the full width at half maximum function. You can see it in the top right corner. I'm sure, I don't really know what the orange looking, I'm sure it's in the Greek alphabet, but I'm not really sure what this entails. I'm sure Gabe could probably explain that to us, but I don't think I will be able to.
Yeah. It's how wide the Gaussian is. You can relate the full width half max to that value sigma.
Oh, okay. That makes a little more sense. Thank you. So this is basically full width at half maximum function. On the left, you obviously have the function, and then on the right is actually on PixInsight. I saw this on a Cloudy Nights forum, and I thought I'd add it. This is basically full width at half maximum as well. And Gabe, I'd like for you to go over the full width half maximum on PixInsight, because I don't have access to PixInsight, so that's okay. So how to detect poor seeing while imaging and also processing. You can obviously look for clouds or haze in the image. This is an image by Astro Backyard, and you can obviously see there's some haze in the image. And actually, there's probably a little bit of light pollution, because you can see those clouds are quite orange. Your DSLR or dedicated astro camera detects haze and clouds much better than your eyes do. Like I like to think of some of those nights when I'm just imaging at like 3 a.m. on a summer night, and it seems like it's really nice out. I mean, obviously star counts are not as great as they had been in nights before, but I don't really notice it. And then I look at my images and there's a bunch of haze on it. This is even more prominent in dark skies when you can't really see the clouds. Like I remember when I was in Bayfield, and it's a Bortle 2, so the clouds were dark blobs, and I didn't even notice them until I looked up in the sky. I didn't even notice them until I didn't even notice the haze in the image until later on after I had already taken the image. Clouds are easily visible, of course, but haze is not as easy. Um, Cameras, obviously, like I said, detect haze more efficiently. And then obviously when you suspect that there is haze, you can look first of all at star counts in the night sky. Like, does it seem like there are less stars? And then also you could look at the basically see if there's any twinkling of the stars at the zenith, and you could also look towards the horizons to see how bad it is. Um, I personally detect haze by looking for halos around the stars or also for bloated stars. You can look at that in the images. I'll show you guys an image later that basically details this very well. Um, we have full width at half maximum eccentricity on PixInsight. Uh, and then there's also image scores. There's probably a lot more that determines seeing, but this is what I found. There's image scores, of course. A lot of stacking programs set scores for each image based on star sizes, star roundness, and then also just star counts and signal to noise ratio. On hazy nights, of course, scores will be lower because stars will appear larger and less round. And then there's also a few examples of software that have these score systems is on Nebulosity, for example. They have the quality score. And then also on Deep Sky Stacker, which is what I use. It's the free software for anyone who doesn't know what it is. They just basically call it score. And then also in PixInsight, they have scores and that basically determine what images are used, specifically when using the Sigma clipping stacking method. So how to detect poor seeing without technology? You want to check for twinkling stars, of course. Stars almost always twinkle near the horizon, no matter the seeing. Like I think of Sirius as an example, doesn't get that high above the horizon. So for most of the time, outside of maybe a very short period of time on really good seeing nights, it is always twinkling, even though it is the brightest star in the night sky. Stars near the zenith may be best in determining overall seeing. So like if you're suspecting haze, you can always look towards the zenith for twinkling stars. And then also check other regions of the sky for twinkling. You may not have equal haze depending on where in the sky you look. So I think it's pretty important that you do that as well. Then also look it to the west. For the most part, I normally the winds and even the atmospheric winds travel from west to east. So always look out towards the west. But this is specific to the mid northern hemisphere, of course. And then also check the west for cloud banks or unusually twinkly stars. Of course, most of the time when you're looking out to the west, towards the horizon, the stars are going to be twinkling, but just look for something that's out of place and unusual. And also like use your sense of feeling, like uh, is it warm or does it feel soggy? Can you feel dew on the ground? This can also determine whether your lens will fog up or not. This is a big problem with DSLRs because generally most people don't have, like with telescopes, you can have those cover things, and then there's also like dew heaters. But with smaller setups, it's less practical because you can't really access it. And yeah, like all of that can be indicators of obstructed seeing. So like if it feels soggy, like just weird, like really moist outside, it's just like it's a good determinant of how seeing will be, or of how seeing may be. And yeah. So some good apps that forecast seeing. I like to use Weather Channel, even though they're not that accurate at all. Like, I mean, obviously meteorologists are not that accurate, but that's not their faults. That's the fact that meteorology is almost impossible to predict. Weather events are almost impossible to predict, but they're below average. But you can still get some decent general forecasts from them. Then there's also Clear Outside, which is my favorite app. You can get the best short term forecasts. They're not that accurate after 4 or 5 days, but in like 2 days, they're pretty accurate. And they have really specific statistics and predictions based on like cloud cover, but also like types of cloud cover. So you have the low cloud cover, mid cloud cover, and high cloud cover. And then you also have like the experimental features, like all the 7T seeing and types of clouds. That's more haze based, and you can get a decent understanding of how the seeing will be. And then you can also get light pollution levels and also moonrise and set times. The moon is our greatest enemies, so it's pretty important that we know about when the moon rises, when the moon sets, how illuminated it is, etc. Then there's also the geostationary satellite server. I don't really use this often, but I know that some of the other members use it before imaging, just to see like what is really going to happen um, towards later in the night, because you can get a decent understanding of like the cloud cover in your region. And then also there's Weather Underground, which you can get like weather forecasts and day and night lengths. I don't really use Weather Underground as much myself, but it definitely is very. I like it for the historical weather. There's a lot. You can literally access any date from like 1932, I think it is. So I think that's kind of cool personally, but I don't really use it for imaging as much as I just use it to browse. And then there's also Pivotal Weather. You can get more weather forecasts on there as well. And then there's also the Clear Dark Sky and Clear Sky charts. I know we have one of those on our website. I use it often. You can get basically comprehensive forecasts that detail sky dynamics like transparency, cloud cover, darkness, seeing, and then also ground dynamics like smoke, wind, humidity, and temperature, all of which affect seeing in their own unique ways. So I said we'd cover light pollution in depth, and we also have a video on this. Dennis, I know you watched that. Um, so light pollution is obviously caused by poor light fixtures. The main culprits are sodium lamps, but LED lights have become very popular as of recently because they're obviously way more efficient than the sodium lamps. And they're way brighter than sodium lamps, so they cause a much they are more they're going to be the main culprits of light pollution in the near future, and I'd say they already are, at least for the increase, because it's been light pollution has been rapidly increasing as of recently. And then the results of that is that fainter stars become harder to see. And like if you've been in a really dark sky, you see that the Milky Way has this just incredible structure. You can see everything, but when you go into like Milwaukee, you probably can't even see the stars of Sagittarius. So how are you going to be able to see the Milky Way? I mean, then also like air glow and zodiacal light become non-existent. Those are very faint, and you only can really see them in those really dark regions, those really dark areas of the world. Obviously, in Milwaukee or Chicago or New York, you cannot see that. To avoid light pollution, astronomers and astrophotographers have came up with some very unique and interesting ways by which they can mitigate the effects of light pollution. So obviously, first is to simply go to rural areas. Uh, there are a lot of rural areas around here. Surprisingly, if you live near Milwaukee, you probably can find decent skies within 30 to 40 minutes away, it's a trek, but it's not terrible. And it's worth it by far. It's very, very much so worth it. And then you can also use a light pollution filter. Like I have the Astronomic CLS. Then there's also like the Astrodon, which those filters are very popular amongst astrophotographers. They have an L2P filter, which is just a light pollution filter. They're also high contrast, so those reds will be really contrasted with the background of the night sky. And then there's also the Optolong L series. So I think of the L Pro, L Enhance, and L Extreme. Those are really nice filters. The L Enhance and L Extreme are narrowband filters. The L Pro is a broadband filter, but all three of them are very useful. And then also you can use a narrowband filter. Those are nicer with more advanced setups. Uh, I, my favorite filter by far is the HA filter. I love that thing to death. Um, the Astronomic makes decent narrowband filters for the DSLRs. I don't really know if many people use those filters for telescopes or for actual big setups, because the Astrodon filters are so much better, and you can get them in 5 nanometers, which is like an extreme narrowband, for much less. But I definitely like the DSLR HA filter, no question. Then also for dedicated astronomy cameras, good narrowband filters are important, and they're made by Astrodon. Astromania is more of a cheap one, but you can probably get decent results out of them. And then there's also Astronomic, but also Radian. The Radian Triad Ultra filter, if you want to spend $1,100 for a piece of glass, well, there you go. Then there's also to access it, you can obviously to access and see light pollution in your area and in other areas, you can use light pollution maps. There's the light pollution map on Dark Site Finder, which I've used for about 2 years. And then there's also the Light Pollution World Atlas, which they just updated it, and it's not as informational as it used to be. You used to be able to see mean magnitude per square arc second, uh, Bortle level, and a bunch of different things. But now you can only see they just made their own levels. It was quite weird. So then there's also some measurements and effects of light pollution, of course. Obviously, a big effect of light pollution is the limiting magnitude, which is basically the darkest or the least luminous star that the human eye can see in a specific area. So in perfect skies, it is around plus 6.5, which is that means you can see about 3,000 stars throughout the year. And it doesn't seem like a lot, but trust me, it is a lot when you go there, when you see a perfect night sky. It can be as high as plus 8 in perfect skies, which you can see that on the right image. But I'm not really sure which one it was, so I just added that one as well. I've been getting very conflicting estimates based on the various sites that determine that, but it's generally believed that it's plus 6.5, which still means you could see 3,000 stars, but obviously you want to be able to see more. We always want more. And of course, like images with good cameras, really good cameras, really long images with a high sensitivity when you're stacking will warrant easily 100,000 stars. But then we live in the city, so we don't get to see what the few in the really dark skies get to see. We only see maybe at best 200 stars throughout the year. I've seen, like in downtown Los Angeles, you can see maybe 5 at any particular time. So that is nothing. That is absolutely nothing. There are more stars in Ursa Major. There are more main stars in Ursa Major than you can see in Los Angeles. Basically, it's terrible. Light pollution is rampant. Even in Milwaukee, can't see that many stars. I can probably only see maybe, if I'm lucky, 100 stars in my own night sky. And I live in a suburb, so that's pretty unfortunate. And even images with good cameras only warrant around 10,000 stars. Now, this excludes some regions of the night sky, of course. Like I think of the Cygnus region, I have gotten 20,000 before, but I had to use the highest sensitivity possible on Deep Sky Stacker to get that. And then also some measurements for light pollution. You obviously have the Bortle scale, 1 being the least. the least amount of light pollution, and 9 being the most amount of light pollution. And then you also have the magnitude per square arc second. This is basically just what it is. It's basically self-explanatory in a way. It's basically the least luminous magnitude at which a star's light will become concentrated to merely a square arc second. So basically, that it'll be visible in a square arc second. That is the least luminous star. So plus 22 is the least luminous star that can be seen in 1 square arc second of magnitude. Obviously, we can't see it, but if we were to use a telescope, we could probably see that star in the best possible place on the surface of Earth. So 22 is the highest that I can think of, because that's what the light pollution atlas says itself. But then you also have Milwaukee, and it's plus 18, which is 39 times brighter than dark skies sites, which is certainly very unfortunate. Obviously, you want darker skies. You want to be able to see more stars, because a lot of the things that come with imaging, at least to me, is the fact that you get to see the night sky when you're imaging. You get to get something out of that night sky. But when you're in a night sky in which there are only 100 stars, in which there are only 100 stars, you're obviously not going to be able to get as much out of that night sky as you would have if you could see 3,000. Then also with imaging, obviously poor signal noise ratio exists as a result of light pollution. And then obviously when there's more light pollution, you don't get as much signal from deep sky objects, especially nebula, because they're easily obstructed in the light polluted fields of Wisconsin, Milwaukee, for example. And then there's also a lot of annoying editing when doing broadband work, like the Astronomic CLS, for example, leaves a terrible color cast that is almost impossible to remove without destroying a fair amount of the light that was gathered in the image um, before getting a decent image. So it's quite unfortunate. So this is just the Bortle dark sky scale. I hope you guys were looking at it while I was speaking. It was obviously the 1 is an excellent or truly dark night sky, and 9 is the inner city sky. Some of us live in 9. I live in a 7, but 9s, I feel your pain. You can't see anything really. I mean, in a 9, you can see nothing. You can't see the Milky Way. It says on here, only the Pleiades cluster is visible to all but the most experienced observers. So you kind of have to know where it is at what time to be able to actually determine it, where it is, to actually see it. And then also only the brightest constellations are visible. So like Ursa Major, Orion, and then also like the fact that the clouds are brilliantly lit. Like you can see them very easily. Even from my night sky, you can see them easily. And often they'll take like an orange color, especially looking towards the southeast. Like I live northwest of Milwaukee. It takes weird, like a weird orange, like almost like a hellish smoky, fiery orange, looking towards the southeast, which is honestly kind of terrifying. And then also the entire sky background has a bright glow, even at the zenith, which the zenith, you normally get the best conditions in terms of light pollution, but that is not the case with a city sky. And then there's also the level 1, which some of us may have been able to see. I personally have not. There you get excellent, truly dark skies, and then obviously the Milky Way shows incredible detail, inspiring detail, and humbling detail. You can even see the Messier 33, which is the Triangulum galaxy. That's pretty impressive because there are numerous galaxies that are brighter than it in the night sky, like Large Magellanic, Small Magellanic, Messier 31. And then also zodiacal light is visible, and it can stretch across the entire sky. Then with air glow and clouds, you can see some air glow near the horizon. You can also see some greenish air glow towards the even all the way up to the zenith. And the clouds are almost impossible to see. I mean, the only way you can see them is by looking up and seeing that there are not stars in the region at which you are looking. That's how I had to determine whether it was cloudy or not on the night that I was in the Apostle Islands. Then obviously the brightness of Jupiter and Venus. It's already annoying to vision in like inner city Wisconsin and inner city Milwaukee, but it's completely different in a dark sky site. It's very annoying. And almost everything is completely dark. So in a way that's kind of terrifying, but in retrospect, you get an incredible night sky. So the next thing I have is actually a video. I'm not really sure how I can actually present this. I'm not sure if there's going to be sound, but yeah, I'll present it. It's a really good video in my opinion. I like the background music, but unfortunately, I'm not really sure if we're going to be able to hear that. But it gives a decent comparison of the night sky in basically depending on the Bortle scale, the Bortle level of that night sky. So let's watch it. Uh, there we go. Okay, well, I'm having a little bit of trouble just gonna start that again. But obviously, I think that's a decent image or video in describing and showcasing the insane differences between a Bortle 9 and a Bortle 1. Obviously, a Bortle 1 is incredibly inspiring, and a Bortle 9 is just a lost in light wasteland. That's why they call it Lost in Light. It's a great showcase of the terrible environmental problem that is light pollution. I don't know why I did that. Okay. So this is an example. This is an example of a Bortle 1 night sky. Copying and pasting images does not get uh, the greatest images, but this is basically what a Bortle 1 looks like. You can see that even though this is a uh, incredible night sky, you can see to the very bottom right of the image that there is still some light pollution. This is even in the darkest of night skies, there's light pollution somewhere. That's that's really unfortunate because of how much we have to deal with light pollution already. Just even the places that we go just to avoid it are even uh, wastelands of light pollution themselves. This is a Bortle 4 night sky. You can obviously see that there is more light pollution, especially towards the horizons. You can see that purple and then also the yellow on the bottom left and then the purple on the bottom right. You can also see some of the lights. That's probably likely LED lights. Obviously, you have the radio tower in the middle. But this is good. This is a good representation of a Bortle 4 night sky. This is a single image of a Bortle 6 night sky. And I think the big thing about this is not a really high quality image, but I think the big thing about this is that you can see the horrible and rampant light pollution that already exists in this Bortle 6. You have these weird color casts, like in the bottom you have the orange, and then even you have the trees in the image. Obviously, the person who imaged this used a star tracker. But you can see as it kind of gets progressively darker towards the top. But even so, there's rampant light pollution. Obviously, that creates these terrible color casts. This is a Bortle 9 night sky, which is the worst possible night sky, of course. You can see this is obviously over a city, and even this entire night sky, even in one of the starrier parts of the night sky, which is, you can see Orion at the top, you don't see that many stars, even in an image. I mean, I'd say there are probably maybe 300 or 400 stars in this image. So it's pathetic in a way. There are so few stars. You can see very little. So this is just another example of the Bortle scale. So obviously in the 8 to 9, you can't see any stars. And then obviously it gets progressively better towards the end. And then at the excellent dark sky sites, it's actually quite incredible even through the image. There are a lot of images that represent it in this way. I think they're pretty important. You can also see the differences in light pollution towards the horizon with the darker, on the darker scale of the night sky. You can see then the rural sky, it's pretty bright, but all the way to the excellent dark sky site, it's even the light pollution on the horizon is quite meager. And then this is just another image of the Bortle scale. Obviously, this is, I believe that's Dubai. And you can't even, there's no star in the image. There's not a single star in the image. This is a Bortle 5, and obviously you can see some stars, and then this is a Bortle 1. And then obviously you can see the entire Milky Way and a decent amount of signal in it for a single image. So I briefly alluded to this earlier, that we'd be discussing wind. Obviously, it's very annoying for temporary setups. The example is the top right corner. I tried to take an image just completely out of the blue of the Great Conjunction. Obviously, the one on the left is not Saturn, Jupiter, and the one on the right is Saturn. You can obviously see that the weird like movement in that trail. It's a 3-minute exposure at 300 millimeters. I don't have that good of a lens, so it's really out of focus. But you can see the weird it should be a straight line, but it's not a straight line, or like at least close to a straight line, but yet it's not a straight line. This is obviously because of wind. I think I took this on December 23rd, and there were wind gusts as high as 40 miles per hour that night. So obviously it was not good, a good night for it. But again, it was the only clear night that week. So what choice do we really have? It can really ruin all hopes of imaging, of course. But yeah, like on nights like that, you definitely do not want to be imaging. But on windy nights, it's more important that you have a sturdier mount. So I said, just the sturdier the mount, the better the image. Obviously, if you have a sturdier mount, it won't be affected by the wind as much. And I mean that I put quotes around as much because it still is affected with temporary setups. but just not as much. Like this is a very meager setup. Like my setup compared to you guys is very meager. Um, so obviously there's going to be more. The imaging is going to be corrupted by the wind more than with more sturdier setups. Obviously, permanent observatories are more important, are very important in keeping away from that wind problem. Obviously, the wind problem is a big problem. So there are two different types that I can think of uh, observatories, of permanent observatories that I've seen before. We only use these types at the Milwaukee Astronomical Society. And I know some of the members who have permanent observatories, they use some of these as well. We have obviously the dome, and then there's also the retractable roof. Domes are definitely the best for defeating that wind. But as Dennis says, they're very annoying to set up. Um, I'm not quite sure why. I kind of like setting up the dome for B scope, but I'm sure that G scope setting up the dome is pretty terrible based on what Tomas and Jeff have told me. Um, Basically, with the dome, the maximum winds can only ever hit a small portion of the dome because of its hemispherical shape. They're often used in housing to basically, like in very windy areas or areas in which tornadoes can occur, to defeat and counteract the effects of the wind in actual domes. And I have a website in my references that will explain this. They actually have the dome houses can actually resist 300-mile-per-hour winds. And obviously, retractable roofs do not have that much of a wind capability. I'm pretty sure you could not image during 300-mile-per-hour winds with a retractable roof. Probably couldn't with a dome observatory either, but let's just say 100-mile-per-hour winds. If you had a really strong observatory with a dome, obviously it would be much more beneficial to have a dome than to have a retractable roof, because you probably damage some stuff with a retractable roof. So how poor seeing affects images. Obviously, clouds increase noise. I have an example of my own image back when, basically this was the first time I ever took an image of the Milky Way. You can obviously see on that image on the right, that on the top right, that there is a significant amount of noise, even more so than the rest of the image in that cloud region right above Jupiter and Saturn over there. You can see, obviously, there's a lot of noise as well, especially color noise. And this is after a significant amount of editing. So obviously, clouds, especially in dark skies, specifically in dark skies, actually, decrease the signal to noise ratio. Then there's also haze and water vapor, of course. It obviously decreases star counts. Obviously, on the bottom, you can see this is an image of Vega and Lyra, like basically just Lyra, a region of the Lyra constellation. You can obviously see that the brighter of these stars, like I think of the double double star and then also Vega, are extremely luminous, even more so than they would be. They're very bloated. Stars appear very bloated, and they glow brighter. I like this image because I think it's really representative of what happens when there's haze or water vapor. This was water vapor. I think I imaged it on October 6th. Yeah, October 6th, 2020, just with a 50 millimeter lens. And you can obviously see that there's some significant haze in that image. This is only a single image. And then also there are some obvious effects on deep sky imaging. I said we discuss each type of imaging, how this would affect everything. Obviously, with deep sky imaging, they're most affected by transparency and not turbulence. It's because you're taking longer exposures. Turbulence is more immediate and occurs not stringently, but it occurs in small bits, small waves. And then also when you have transparency issues, you're gonna see bloated nebula, and obviously as a result, lower signal noise ratio. And you don't want bloated nebula because you want to get decent, strong detail in the nebula, especially for when you're editing. So some effects on lunar imaging. Haze and fog can make it very hard to extrapolate the mares and the craters on the moon. And then also turbulence can make certain regions of the moon appear bloated or blurry. I like to think when I was looking with the ZIT observatory, I think it was the 10-inch Meade in the front of the observatory. I was looking at the moon through that. It was a waning gibbous moon, and I was seeing those weird like dancing the dancing translucent butterflies. Basically, like it reminds me of basically when like it basically reminds me of heat. Like you see the like extreme heat, it almost appears like a vibrational weird pattern right above the place where the heat exists. That's basically what's happening in that atmosphere. It all has to do with convection and uneven temperatures in that region in which you are looking. Then also effects on planetary imaging, similar to lunar imaging. Obviously, turbulence affects it significantly. And like Mars, for example, they can appear fuzzy on even average nights, specifically in Wisconsin. Average night in Wisconsin is not a good night. But yeah, it's generally most affected by turbulence and convection, not as much transparency, but obviously transparency does have an effect on it. Planetary imaging is much harder than deep sky imaging when it comes to seeing. You want to be in those really incredible skies to get decent signal. And then also you have to deal with the rotation of the planets, which that's with quickly rotating planets, that is not easy. And then of course, turbulence can make seeing details on a planet impossible. Again, I'm going to refer to this again the day after Thanksgiving at a scope, trying to look at Mars. Not easy. The seeing conditions were not great. There was a significant amount of turbulence. But yeah, so how to counter poor seeing while imaging? I believe this is actually my last slide. If seeing is terrible, of course, just do not image. In Wisconsin, we don't have many nights to image, so this is not as much of this is kind of a heartbreaker, but on terrible nights in which it's almost really not worth it to image, just don't image. Don't waste the time to bring all your equipment out just to have to bring it back in. Obviously, patience is a virtue, but in Wisconsin, you don't really have that many virtues. So you don't have many really good night skies. So it's a little more difficult here. Obviously, another way to counter it is to basically use cooled cameras and telescopes. The cooled cameras are very useful, of course. They basically use fans to blow out uneven temperatures and keep cameras and telescopes cool. I believe it's like 20. I believe they set it at like 20 Celsius below the temperature of where they're at. It's either that or negative 20 degrees Celsius at f scope. And then obviously cooled cameras experience far less noise than uncooled cameras. I think of my own DSLR. I have a full spectrum T3i, and I don't get the noise on my images is significantly worse than the f scope 1600, the ASI 1600 on f scope. The images from that are significantly better, and I'll show you examples of that right after this. And then also you can just check the forecast, like travel to places with better seeing. Like you can always look at the forecast. I know CBS Sunday Morning has decent US wide forecasts that show like areas of high and low pressure, and also like all that cool stuff. You can even see it on the very left, like crystal clear and cool, but poor seeing. Like it's fully dependent on the weather conditions in the entire region. It's not only based on clearness and like how sunny it is or like how clear it is. It's based on many other things, of course. You want areas of high pressure, not areas of low pressure necessarily. But yeah, just check the forecast, and then obviously try to go to drier areas. I know we have some members that are in drier areas, and they definitely They're definitely indulged in the advantages of being in a desert night sky. They're obviously significantly better than Wisconsin night skies. Then also avoid tropical regions during their monsoon seasons because, first of all, it's not going to be clear that often. And second of all, there's going to be a lot of water vapor in that sky. So you're not going to have that great of seeing conditions. For traveling, though, obviously you can't do anything with COVID, but I think of the Mojave and Atacama deserts that basically present the best seeing conditions. Even the Atacama itself, it has 330 clear nights a year, which is absolutely incredible. And that's obviously out of 365. So obviously, uh, over 90% of the nights are clear, which is incredible. This is actually the bottom image is of the night sky, the winter night sky, well, their summer night sky in Chile, which is where the Atacama Desert is located. And then on the top, you have the ASI 1600 millimeter Pro or 1600 mm Pro, not millimeter. That's what's used on F-Scope. It is my favorite camera ever, but I'm sure there are better cameras than that. It's still my favorite camera ever because uh, it's associated with the observatory, right? So this is basically an example. These are my own images. These are examples of DSLRs versus an actual imaging rig and with a 1600 mm Pro. On the left is 4 hours of imaging, and on the right is an hour and a half. And even with darks and all that, I set darks for the one on the left, and even so, you can obviously see that there is significantly more signal and a fairly better image out of an hour and a half with the dedicated Astro camera versus the T3i. Granted, the T3i is quite old, but
Hey, William,
yes,
is the one on the left taken through an HA filter? Or is
yes,
that
they are
broadband?
both taken through HA filters.
Okay.
The only difference between the two filters on the in these images is the one on the left is a 12 nanometer and the one on the right is a 5 nanometer. I was using the Astronomic HA 12 nanometer filter, and then the one on the right, I was using an Astrodon 5 nanometer HA filter. So obviously you're going to get better images anyways with the 5 nanometer filter. But even so, there's significantly more signal in the F-scope image based on the Orion, just general Orion image. And this is a little bit more accurate, in my opinion, of the detail that comes out from based on modified camera versus actual dedicated astronomy camera, because obviously the field of view is very similar. You may recognize this image on the right because it was taken by one of our members, Chad Andrist. That is the Venus conjunction, it can be said, with the Pleiades. And then on the left is Trevor Jones, or Astro Backyard's image of the Pleiades. And the big difference between the one on the left and the one on the right is that the one on the left, it was taken with a DSLR. It was taken with the 60DA, which is a very popular, technically dedicated, but it's really more of a modified DSLR. And then the one on the right was taken with the ASI 294 MC, which, in my opinion, yielded a much better image of M45 than even Trevor Jones got. The signal is much stronger, and there's a more accurate color. I really like that light blue. It's similar to the light blue that you should get, and it just looks more visually appealing, in my opinion, personally. Yeah, it looks much better, and the colors are much stronger with that ASI 294 than with Trevor Jones's 60DA. That's pretty much it. That is it. I'm going to send the actual presentation itself to the MAS Google group so that they can access it, because I think the links are very important. And then also the video. I don't know if you guys were able to hear the sound with it, but I definitely would recommend watching it again, because I watched it probably 15 times in the last year or so, and every single time I like it more. It's weirdly and oddly inspiring. just based on that incredible night sky. So yeah, that's it. Thank you guys for listening to me for this.